All right, so in this example, this is going to be our most challenging example. Our answers are going to be kind of ugly fractions. And so I want to show this example to show you a nice strategy to not have to worry about crazy fraction answers. And that's actually the beauty of using this addition method. Now, as I look at this, we got to say, all right, well, I need to somehow make my x's opposites or else my y's opposites. If I want to make the x's opposites, I can't simply multiply 4 by something to make it up to 6 without being a fraction. Similarly, I can't look at the y's and say I can't multiply 5 by something to bring it up to 6 without making some fractions. What I can do, though, is I can multiply both equations by something to make the values match up. So for instance, with the x's, if I want to get those guys to match up, I could bring them both up to 12s. So I could multiply the first equation by a 2 and the second equation by a 3, and that would bring both of the x's up to 12x. Now, I got to be careful though, because I actually want them to be opposites. Not right now they're both 12x. I want one of them to be negative 12x. So I need to change the sign of one of these. Currently, for the y's, we're looking at negative 10y and negative 18y. So let's go ahead and make the bigger one positive. So let's change the sign of the 3 there. Let's check out what this looks like for both equations. We're going to distribute the 2 across the first to get 12x minus 10y equals 14. We're going to distribute negative 3 across the second. That's going to get us negative 12x, positive 18y, and negative 21. Okay. Now we're set to add these together. 18y minus 10y is 8y. Negative 21 plus 14 is negative 7. I get negative 7/8 for my y. Now, one of the things I really want to point out here that's really cool about this is we do have a fraction answer for y, but we never had to deal with fractions. The fraction didn't come in until we said, all right, I got this negative 7 on the right, divide by 8, bam, there's a fraction. We didn't actually have to deal with fractions. That's kind of cool. Now, if we go through our normal steps, we'd plug this negative 7/8 back into one of those equations, and then at that point we'd have to deal with fractions. That kind of sucks. But I'm going to point out that we don't really have to do that. We could start back at the original problem. And if you look at what we did do, we eliminated the x's originally, and that allowed us to solve for y. We could go back to the original problem and eliminate the y's and solve for the x. And that's actually what I would suggest that you do in a problem like this. Let's rewrite the original problem. But now instead of multiplying by something to get rid of the x's, let's multiply by something to get rid of the y's. If I brought the y's both up to 30s, well, right now they're negative 30, so I need to make one of those guys positive, one to be negative. So let's go ahead and change the sign of that one. Let's distribute those across and see what we get. We get 36x minus 30y equals 42. We get negative 20x plus 30y equals negative 35. Now when I add these together, I'm going to get 16x 0y equals 7. Divide by 16, and I get 7/16. I now have the ordered pair 7/16 negative 7/8. Very gross looking fractions, and I never had to deal with fractions anywhere in the problem. That's pretty cool. So that's one of the cool things about this addition method is that we can have this answer that has crazy fractions and never deal with fractions throughout the problem. Pretty cool.